The next thing we're going to look at in section 8.1 is the definition of a fundamental set of solutions. Any set of n linearly independent solution vectors of the homogeneous system on an interval I is said to be a fundamental set of solutions on the interval. So if we have a system of n linear differential equations in n variables, and we have solution vectors x1 through xn, if each one of these xi's is a solution, and furthermore if they are all linearly independent, then the collections of those x's form what we call a fundamental set of solutions. Theorem 8.14 does tell us that a fundamental set does exist for the homogeneous system on an interval I that we're looking at. As long as all of the individual functions are defined and continuous on I, then a fundamental set of solutions does exist. And not only does it have to be continuous, but in addition they need to be differentiable on the I, then we will be able to find a fundamental set. Theorem 8.15 then discusses the general solution of the homogeneous system. One of the things that we recall from superposition is that if each of these xi's is a solution of the system, then it's true that their linear combination will also be a solution to the system as well. And if you have the linear combination of vectors coming from a fundamental set, then that's what we refer to as the general solution. So the general solution to our system is simply the linear combination c1x1 plus c2x2 up to cnxn of our solution vectors from our fundamental set. We can highlight this in the next two examples. For instance, if we take a look at example 2, we had example 5. Way back in example 2, we had the following system. So if we go back and look at example 2, we were looking at the system x prime is equal to 1, 3, 5, 3x. We showed that both x1 and x2 in previous problems are indeed solutions of the system. Furthermore, in another example, we showed that these two solutions also happen to be linearly independent. This was a 2 by 2 system, so n was equal to 2. Therefore, the collection of x1 and x2 does form a fundamental set of solutions for this differential system on the interval negative infinity to positive infinity. Therefore, we can discuss the general solution. The general solution x is just going to be the linear combination of those two. So it's going to be c1x1 plus c2x2, which is equal to c1 times our x1 solution plus c2 times our x2 solution, and that would be our general solution for that system. Let's take a look at the next example. In example 6, they ask us to show that x1, x2, and x3 form a fundamental set of the system x prime equals ax on negative infinity to positive infinity. In a previous problem, we've already shown, I believe it was at least two of these. I believe x1 and x2, we've already shown our solutions to the system. I'll leave it up to you on your own to check. Take the x3 derivative, plug it into this differential equation, and show that this system will also, the solution vector will also be a solution. So we know that we have three solutions to this 3 by 3 system. To show that it's a fundamental set, it would remain to show that that these three vectors would be linearly independent. And in order to show that they're going to be linearly independent, what we want to do is calculate the Wronskian and show that the Wronskian is going to be non-zero on this interval I, which is from negative infinity to positive infinity. So let's go ahead and do that. Remember, the Wronskian is simply the determinant of the matrix whose columns are x1, x2, and x3. This is cosine t minus 1/2 cosine t plus 1/2 sine t, negative cosine t minus sine t. I'm going to need to make this bigger. Our next column is going to be x of 2, which is 0, times e to the t. So at 0, we get e to the t, and then 0. And then our last column is x3, which is sine t, negative 1/2 sine t minus 1/2 cosine t, and then negative sine t plus cosine t. So now we need to calculate this 3 by 3 determinant. Some of you might remember from perhaps Calculus 3 or maybe a class in matrix algebra or linear algebra, but we can use cofactor expansion to do this. If I expand about the first entry, so the pivot is going to be cosine t, so I'm going to have cosine of t times the submatrix, the 2 by 2 submatrix, which is going to be given by et negative 1/2 sine t minus 1/2 cosine t, 0, and then negative sine t plus cosine t. When we move on to the next entry, be very careful. It alternates in sign, so minus. Now we're going to expand about this next pivot. So what we would have would be a this term, negative 1/2 cosine t plus 1/2 sine t, negative cosine t minus sine t, and then we have a negative 1/2 sine t minus 1/2 cosine t, and then we have negative sine t plus cosine t, and then the next sign will be back to plus. We're going to expand about the last pivot, and also don't forget, I forgot to put my coefficient there, which is going to be 0. So we expanded about this one, so it's a 0 out in front. And now we're going to expand about the last pivot, so we have a sine t out in front. And it's going to look like this. So we have a negative 1/2 cosine t plus 1/2 sine t, negative cosine t minus sine t, and then we have an e to the t and a 0. Let's continue to plug through. Let's see if we can calculate this function. So this is going to be equal to, we have the cosine of t times, now with this part, again with this part, the 2 by 2 matrix, you're going to have e to the t, which is the major diagonal, times negative sine t plus cosine t minus, thankfully this whole diagonal is going to be 0 because of this entry. So that's the first part. Luckily, when we did our expansion, this whole term was 0. So no matter what you get when you do this 2 by 2 determinant, this whole next term is going to be 0. And now we have plus, we have our sine t, and now we need to do this expansion. So this diagonal times 0 will give us 0, minus, now we have e to the t, which is going to get multiplied by negative cosine t minus sine t. Let's go ahead and expand as much as we can. So we have cosine t times negative e to the t sine t plus e to the t cosine t plus sine t times, this will be an e to the t cos t plus e to the t sine t, which is equal to negative e to the t cos t sine t, distributing, plus e to the t cos squared t, plus distributing, e to the t cos t sine t, plus e to the t sine squared t. And now to simplify this, notice that these two terms cancel. We have a negative e to the t cos t sine t, and we have a positive e to the t cos t sine t. So those two cancel. What's left over is these two terms, and they both have a common factor of e to the t. We pull that out, and we get cosine squared t plus sine squared t, which we all remember from trig. It's the Pythagorean identity for 1. And so we get e to the t. So we've gone through and we've calculated it. And what we have now is the following. The Wronskian of x1, x2, and x3 is equal to e to the t. And one of the things we know about the exponential function is it is never 0. And so we've already shown previously that x1, x2, and x3 are solutions. This just shows that x1, x2, and x3 are also linearly independent, and thus they form a fundamental set of solutions. And therefore we can talk about the general solution. I'm not going to rewrite it, but the general solution of this system is simply going to be x equals c1 x1 plus c2 x2 plus c3 x3. General solution namely being the linear combination of a fundamental set of solutions. In theorem 8.16, we're going to talk about the general solution of a non-homogeneous system. Let's let x of p be a solution of the non-homogeneous system on an interval I, and let xc be equal to a linear combination of our fundamental set. Then the same thing that we saw with the preliminary differential equation stuff, the simple linear differential equations, will also be true of systems. In general, the general solution to a non-homogeneous system is simply going to be yc, which is the complementary solution, which is the solution to the homogeneous system, plus this x of p, which is going to be the particular solution, which is the part which is associated to the non-homogeneous differential equation. So there's this really nice analogy and this really nice connection between the way that we solved simple singular differential equations and the way that we solve systems, in that typically the general solution is found by finding the complementary solution first, which is the solution of the homogeneous part, and then adding in x of p, which would be the solution to the non-homogeneous